conditioning is critical in maintaining proper operation of a hydraulic system. In this course, you will learn about different types of filters, their location, and how they keep hydraulic fluid clean. You'll also learn about the importance of regulating the temperature of hydraulic fluid with devices like heat exchangers. For example, fluid that is too hot or too cold can have a negative impact on system performance.
Cleanliness of hydraulic fluid has become critical in the design and operation of fluid power components. With pumps and valves designed to closer tolerances and finer finishes, fluid systems operate at ever-increasing pressures and efficiencies. These components will perform as designed as long as the fluid is clean. Oil cleanliness results in increased system reliability and reduced maintenance.
As particles are induced or ingressed into a hydraulic system, they are often ground into thousands of fine particles.
These tiny particles are tightly packed between valve spools and their bores, causing the valve to stick. This is known as silting. To prevent silting, early component wear, and eventual system failure, engineered filtration is required. Engineered filtration includes understanding required micron rating, application of the beta ratio, maintaining proper ISO code cleanliness levels, filter location specific to the system design and environment. Micron is the designation used to describe particle sizes or clearances in hydraulic components. A micron is equal to 39 millionths of an inch. To put this into perspective, the smallest dot that can be seen by the naked eye is 40 micron. Consider the following illustration. If we looked at a human hair magnified 100 times, the particles you see next to the hair is about 10 micron. Industrial hydraulic systems usually filter in the 10 micron range. This means that filters are filtering particles that cannot be seen by the naked eye. Filtration devices are used to filter particles out of the system's fluid. A filter's efficiency is rated with a beta ratio. The beta ratio is the number of particles upstream from the filter that are larger than the filter's micron rating, divided by the number of particles downstream larger than the filter's micron rating. In this example, there are 200 particles upstream which are larger than 3 microns. These flow up to and through the filters. A filter that allows more particles through, or in other words, one that is less efficient, has a low beta ratio. You can see that the filter at the top allowed 100 particles through. The filter on the bottom allowed only 1 particle through. If we apply these numbers to the beta ratio formula, we can see that the filter at the top has a lower or less efficient beta ratio, and the filter at the bottom has a higher or more efficient beta ratio.
To specify the cleanliness level of a given volume of fluid, we refer to what is known as an ISO code or ISO solid contamination code. This code, which applies to all types of fluid, provides a universal expression of relative cleanliness between suppliers and users of hydraulic fluid. Based on a milliliter of fluid, a particle count is analyzed using specific sizes of particles, 4 micron, 6 micron, and 14 micron. These 3 sizes were selected because it gives an accurate assessment of the amount of silt from 4 micron particles and 6 micron particles, while the number of particles above 14 micron reflect the amount of wear-type particles in the fluid. To interpret the meaning of these results, a graph like the one shown would have been consulted. In this example, a rating of 22, 18, 13 indicates the following. The first number, 22, indicates that the number of particles greater than or equal to 4 micron in size is more than 20,000 and less than or equal to 40,000 per milliliter. The second number, 18, indicates that the number of particles greater than or equal to 6 micron in size is more than 1,300 and less than or equal to 2,500 per milliliter. The third number, 13, indicates the number of particles greater than or equal to 14 micron in size is more than 40 or less than or equal to 80 per milliliter. This ISO code is meaningful only if we can relate it to the required cleanliness level of our hydraulic system. This is usually based on a manufacturer's requirement for cleanliness levels in which a component may operate. For example, most servo valves require an ISO code of 15-13-12 or better, while gear pumps may operate adequately in fluids with 18-16-15 ISO.
Filter placement is critical for maintaining acceptable fluid cleanliness levels. adequate component protection, and reducing machine downtime.
Filter breathers are critical in prevention of airborne particulate ingression.
As the system operates, the fluid level in the reservoir changes. This draws in outside air, and with it, airborne particulates. The breather filters the air entering the reservoir. Pressure filters are often required to protect the component immediately downstream of the filter, such as a sensitive servo valve, from accelerated wear, silting, or sticking. Pressure filters must be able to withstand the operating pressure of the system, as well as any pump pulsations. Return filters best provide for maintaining total system cleanliness depending on their micron rating. They can trap very small particles before they return to the reservoir. They must be sized to handle the full return flow from the system. A kidney loop or offline filtration is often required when fluid circulation through a return filter is minimum. Being independent of the main hydraulic system, offline filters can be placed where they are most convenient to service or change. Offline filtration normally runs continually. In this learning lab, you will learn the proper placement of filters. A description explaining a filter's placement will appear at the right side of your screen. Click and drag the description to the proper filter area. Temperature control is critical in hydraulic systems. Even with the best circuit design, there are always power losses in converting mechanical energy into fluid power. Heat is generated whenever fluid flows from high to low pressure without producing mechanical work. Heat exchangers may be required when operating temperatures are critical or when the system cannot dissipate all the heat that is generated. There are two basic types of heat exchangers. Each is based on a different cooling medium: water-cooled heat exchangers and air-cooled heat exchangers. If cooling water is available, a shell and tube heat exchanger may be preferred. Cooling water is circulated through a bundle of bronze tubes from one end cap to the other. Hydraulic fluid is circulated through the unit and around the tubes containing the water. The heat is removed from the hydraulic fluid by the water. There are advantages to this type of cooler. They are the least expensive, they are very compact, they do not make noise, they provide consistent heat removal year-round, and they are good in dirty environments. The disadvantages are water costs can be expensive. With rupture, oil and water may mix, and usually require regular maintenance from mineral buildup. Air-cooled heat exchangers consist of a steel radiator core through which oil flows while a strong blast of air passes across the core. In industrial applications, the air is pushed by an electric motor-driven fan. The advantages of this type of air-cooled heat exchanger are they eliminate problems associated with cooling water, they have low installed costs, and the dissipated heat can be reclaimed. The disadvantages are there is a higher installation cost, noise levels range from 60 to 90 decibels, and they are larger in size than comparable water-cooled equipment. In addition to holding the system fluid supply, the reservoir serves several other important functions. It cools the hydraulic fluid. This is accomplished by dissipating excess heat through its walls. It conditions the fluid. As oil waits to leave the reservoir, solid contaminants settle, while entrained air rises and escapes. The reservoir may provide mounting support for the pump or other components. A well-designed hydraulic system always includes a properly designed reservoir. An industrial reservoir should include the following components: a baffle plate to prevent returning fluid from entering the pump inlet, a cleanout cover for maintenance access, a filter breather assembly to allow air exchange, a filler opening well protected from contaminant ingression, a level indicator allowing upper and lower levels of fluid to be monitored, and adequate connections and fittings for suction lines, return lines, and drain lines. It is often stated that the hydraulic fluid is the heart of the system, or the most important component. The reservoir serves a critical role in maintaining the efficiency of fluid transfer and conditioning.